All right. Well, good morning. Um, Thank you for joining me online today. And I just want to kind of give you a brief update. Looks like people are participating and making submissions for the regression competition. We've got 111 submissions so far. And I expect this will grow very quickly and very rapidly. There's 4 days to go. I do want to encourage you to make frequent submissions to see how they go. So that you know, continue working on them and then make submissions. Regarding the leaderboard, remember there is a public score and a private score, and they will not necessarily be the same. So it's not always the best strategy to try to make your public score, the absolute best possible, because you might end up choosing a model that overfits the public score and doesn't quite generalize to the private score. So, just do be aware of that. We are getting a variety of submissions, and this, I think this is a baseline where I just did a random forest. So my hope is that through recipes and a few different kind of models and whatnot, you can get improved performance there. So keep working on that. The regression competition will close, um, at the end of this week. And then the classification competition doesn't look like there's very many teams or participants. So, make sure you sign up, register for that and form your teams and start making submissions for that as well. And that's the classification, and that will close next week. All right. Um, I have a kind of a shorter lecture planned for today. I want to cover this concept of ensembles of models, okay? And so there's a package called Stacks, and this is part of Tidy Models. And so um, I would, you can go to stacks.tidymodels.org. If you go to tidymodels.org, that will take you to um, the reference for the tiny models, and then Stacks allows you to create ensembles. Okay. And so basically, the way it works is you're going to define uh, different models, and you'll kind of train them. And then the ensemble is going to be kind of a collection of all of the different models that you've made, and it will as you when you train your ensemble, you're going to give some of your models, your better performing models, um, more voting power. And then, but you also won't just completely throw away every single other model. You will have the other models will maybe get, a partial vote or something like that. And so you create, um, a a stack object, basically an ensemble, a collection of these different models, and then when it comes time to make predictions, you combine their predictions with blend predictions, right? So it's going to kind of you'll add or remove candidate models, you'll blend the predictions, and then use that to make predictions. Okay, and in the past, all of the winners of the competitions have all used stacks. So it does seem to have material benefit as far as improving your predictive performance. So I do recommend that everybody try out using a stack, using stacks of models. And we'll walk through this. I do think this will improve your predictions. So anyway, um, you install it by running install that package as stacks. I think I've already have it on mine, but you'll run that, and then it downloads and installs, and then we'll walk through kind of how this process works. Okay. And so Stacks is part of not tidy models. So basically, if your model works with tidy models, it should work with Stacks. Okay. And so it says, any model type implemented in Parsnip or an extension package is fair game to add to a Stacks model stack. And basically, um, Stacks just is kind of like a meta package on top of everything where it just takes um, models, the predictions made by some other trained model that you've created via Parsnip or your workflow or your recipe workflow set or whatever it might be, and um, and then it kind of figures out just a way to blend the predictions. Okay. Any resampling algorithm. So, we use cross-validation as a way for us to evaluate our performance, and then any metric implemented in Yardstick, root mean squared error or any other kind of um, uh, error metric that we're using can work there. Okay. Um, So it says at the highest level, ensembles are formed from model definitions. And it says model definitions are an instance of a minimal workflow containing a model specification and optionally a preprocessor as defined in the recipes package. And it could be as simple as which variables are you going to use? Okay. Model definitions specify the form of candidate ensemble members. And so for the example on this kind of tutorial page or the introductory page, they are looking at three different, I guess, types of models. You have k-nearest neighbors, you have the linear regression model, and then a support vector machine model. Okay. It says a diagram representing model definitions, which specify the form of candidate models. And we have k-nearest neighbors, linear regression, and a support vector machine. And then to be used in the same ensemble, each of these models definitions must share the same resamples. Okay, so the the R sample R set object, when paired with the model definitions, can be used to generate the tuning or fitting results object for the candidate ensemble members with tune. So we use resample to form our cross validation. Okay, and you might have different kinds of models that are candidate models. So here we have four different k-nearest neighbors models. So you could have, k-nearest neighbors with using 5 nearest neighbors or 7 nearest neighbors or 13 nearest neighbors or something like that. So you might have different candidate members, and then you might also have different kind of support vector machine models, candidate members. So, um, for example, as you can tune your gamma or your cost parameters. So with support vector machines, you have these different parameters, and so we have a total of in total 11 different candidate members. Okay, so we have four different k-nearest neighbor members. We have one for the linear regression model, and then we have 6 different support vector machine um, potential candidate members. And so um, we take these different candidate members and we add them to our data stack. Okay, so we create a data stack object. This is um, the kind of the object that our stacks package uses. Okay, and it just kind of organizes all of these different things into a tibble. Okay, and so These, the first column gives the true outcome in the assessment set. So you have these, um, when you do cross-validation, it will say, all right, these are the different outcomes, and then it shows what are the outcomes produced by these different models. Okay, so it says the first outcome gives the true outcome in the assessment set. All right, and then the remainder column gives the predictions from each of the candidate ensemble members. All right, and and it says, yeah, when the outcome is numeric, there's only one column per candidate ensemble member. Classification requires as many columns per candidate as there are levels in the outcome variable. So, you know, we're going to just look at a regression one where it's just producing numeric. But if it's a classification and you have, I don't know, you're classifying three different colors or something like that, it'll say like, which ones did Canon guess red and which ones did Canon guess yellow and which ones did Canon one guess blue and so on and so forth. Okay. There's a few other additional things. And then the stacks model is going to take these and figure out how best to blend them. Okay. So it says that this this diagram represents a data stack, which is a kind of data frame, and it says the columns depict the different values of the outcome variables. Okay, so we have the true outcome variable as well as the predictions made by the different candidate models. Okay, and then we evaluate this using the function blend predictions, and it says. And it's going looking at all of the different predictions made by these different models. It says, okay, what's the best way to kind of combine these different predictions to predict the outcome? Okay, so if you have, um, you have these 11 different models, and all 11 of them are each trying to predict the same outcome, but in slightly different ways. Okay. And so from here, it's just kind of like, all right, now that I can see how everybody's predicting, we can say, all right, if I wanted to predict something in the future, can I combine some of these things? Okay. And so, um, yeah, it's kind of in, in in the same way that you have these different, like in linear regression, you're using each of these different variables to make predictions, and you kind of adjust your um, coefficients to best predict the outcome. Now it's like you have a higher level, you're like another layer abstracted in that you have these different kind of entire models that make predictions, and you're still trying to kind of fine tune that, right? And so that's blend predictions, and or we call that meta learning, right? And it says, all of these outputs are going to be highly correlated because they're all trying to predict the same thing. And so, depending on the degree of regularization you choose, the coefficients of the input, for many of these things, they will zero out, okay? And their predictions will end up having no influence on the final output. But some of them will. And so here it says, just for example, this is a diagram representing the stacking coefficients, and it says, how much of each of these members get kind of influence. So some of these got zeroed out. They will have no influence on the final output, but some of them do have coefficients associated with them. Okay. And so that's how we are going to create a stack. Okay. So diagram representing the stacking coefficients, the coefficients of the linear model combining each of the candidate members' predictions to generate the ensemble's ultimate predictions. So we're going to treat each of these things as its own kind of predictor in the uh, like in a final kind of linear model. We're going to take each of these things and combine them. Okay. And and so anyway, that's that. And this will form our model stack. and then we use that to make our predictions. So we'll walk through an example. Okay, this is just their kind of tutorial example that we will use, and you can then apply the same kind of idea towards your projects. Okay, so we'll load everything up with library tidying models and library stacks. Okay, and then as far as the data set we're going to use this data set called tree frogs. Okay, and so you can take a look at the tree frogs. And it says, the red-eyed tree frog embryos can hatch earlier than their normal 7 days if they detect potential predator threats. And researchers want to determine how and when these tree frog embryos were able to detect stimuli from their environment. To do so, they subjected the embryos at various developmental stages to predator stimulus by jiggling the embryos with a blunt probe. Beforehand, though some of the embryos were treated with whatever, some kind of compound, gentamicin, compound that knocks out their sensory organ. Okay. And then so the researcher and they found that these factors inform whether an embryo hatches prematurely or not. Okay. So, they have these different variables. These are kind of like their collection, were they in the control or gentamicin? Um, I guess reflex is the different nerve or something, and then we're looking at hatched, yes or no, the age, I don't know, time of day, latency, all of these different things. Okay, and so one is where when they didn't hatch, okay, we're going to get rid of these. So, because we can really only analyze the ones where we measured uh, the ones that did hatch, okay? So, we'll subset this, okay? We're going to get rid of anything where um, the tree frogs didn't hatch, okay? So, there's quite a few are going to get removed, okay? And then we're also going to remove like these ID columns on Clutch. So after doing that, okay, now we're down to 572 rows, okay, and we have um, these different variables, okay, and so we're looking at um, just what is the time to hatch as measured by latency, okay? And then we can also look at the embryo of the age of the embryo, along with whether they were treated or not, okay? And so just kind of this is just some exploratory analysis to see, is this even a relationship that we should explore here, okay? Okay, so this is the same kind of plot here, all right? And so we can see, yeah, you know what? Um, as when they were kind of treated with this, we can see um, the there's definitely some kind of relationship, okay, between the age of the embryo, the time to hatch, um, and we see, there is some kind of relationship, right? So we're trying to predict out latency, the time to hatch based on the other attributes. And so it looks like, yeah, as the embryos kind of get older, their time to hatch looks like it's reduced. It does seem that those that were treated with gentamicin, and so that they're, um, I guess they're knocks out their sensory organ. Okay, it does seem like they are hatching later than those that were in the control group. Okay, and that seems to be a true for those down here as well as over here. So anyway, um, can we fit some kind of predictor to try to predict the time to hatch? Okay. So again, what we're going to do is we're going to form a few different candidate models, and um, and then we will, you know, uh, fit each of those separately, and then we'll combine them in a stack. Okay. So we have these different model definitions. We're going to have the k-nearest neighbors, linear regression, and support vector machine models. In order for us to evaluate all of this, we're going to create folds. So we're going to first set up um, we're going to first set up the what do you call it? Train test split. Okay. So we'll do our initial split, and that will form the training set and the testing set. Okay. And then after that, we will do V-fold cross-validation. So we're going to have five-fold cross-validation among just the training data. Okay. So looking at, so in the full data set, we have 572 observations. Okay. In our training set, we have 429. We leave 143 in our test set. Okay. And then we're going to do V-fold cross-validation. And so with V-fold cross-validation, we're going to have five folds, okay, made out of the 429. Um, as far as our recipe goes, as far as the preprocessor goes, it's just going to be like the most basic one, where it just says predict latency based on the other variables. Okay, so we're going to predict latency based on the other four variables. And then our metric set will just be um, root mean squared error. Okay, so this is about as um, basic as we can have. Let me respond to this message. Okay. Okay. Um, so so this part I'm hoping looks very familiar in terms of the train test split and then the V-fold cross validation, right? So this is kind of um, from our textbook we have this thing, right? So we have the initial split that splits between training and testing, and then with our training data, we do five-fold cross-validation, which will give us five different resamples here. Okay. Um, as far as the different kind of controls that we have, there are options that you can use as far as controlling how the stack goes, and the tune grid and fit resamples. So as we try to tune our parameters, we use tune grid, or we can kind of do like the search term tune iterative search as far as tuning our hyperparameters and things like that. And then the way it gets evaluated is using with fit resamples. So, um, so anyway, those we can use the kind of default things. Okay, we have control wrappers as far as how it works for the stack, since we wrap these things up in here, and we'll set them up. Okay. So our control grid as controls for our grid and controls for our resampling. And you can kind of take a look at those. But basically, the defaults will be that like verbose is going to be false, allow parameters true, extract will be left blank, and all of these things. Save predictions, save the workflow. And if you want to change any of these, you can change any of these options here. Okay. So these are kind of the default control settings. And then we will set up our different models. Okay. So we are going to have the k-nearest neighbors model. Okay. And so as far as the k-nearest neighbors, we'll specify using parsnip's nearest neighbor to say we're going to do this. And then we're using it to make predictions using regression. And then we are going to leave, how many nearest neighbors, okay, as a tunable parameter. So our k-nearest neighbor specification is going to be this. We'll use the engine KKNN. And so we can see we have a tunable parameter here, which is going to be how many neighbors that we'll have. All right, and says note that since we are tuning over several possible numbers of neighbors, this model is going to define multiple model configurations, and the specific form of those configurations will be determined when specifying the grid search and tune grid. Okay, and it says we can expand our recipe, so we have just the basic recipe, which just says predict everything. I mean, predict latency based on everything else. And so for k-nearest neighbors, that requires numeric inputs. So we're going to uh, write a recipe that's going to work with k-nearest neighbors. And so we're going to take kind of the basic recipe, which just says predict latency based on the other things. And then all of the nominal predictors. So as far as tree frogs, we have time of day, reflex, and treatment. We're going to have to make these dummy variables. Okay. And then after we do that, we'll remove anything that has no variance. Step ZV removes, looks at all of the predictors and says if any of these predictors don't vary at all, remove them. I don't think this really gets affected. If we're missing values, we will impute the mean. Okay. And then for all of the numeric values as well, we will normalize all of them so that they have, uh, a mean of 0, standard deviation of 1. Okay. And so you can look at the recipe itself, but it says, yeah, we're predicting latency. We've got 4 variables, and then these are the operations that it's going to apply here. Okay. And then we combine them into a single workflow. Okay. So our workflow, we have a empty workflow. We're going to add our model, the k-nearest neighbors model, and then we'll add our recipe. Okay. And so this is going to process all of our data and allow us to kind of fit and make predictions. All right. And then, so as far as our grid goes, we're going to try out, we're going to call tune grid. Okay. And so tune grid will have 4 different values to try out for um, the value of k here. Okay. And so it says we're going to do this using 5-fold cross-validation because we're using our the v-fold cross-validation, our folds that we defined here. The metric is we're using RMSE. Okay. And we have everything else there. So this is going to fit k-nearest neighbors 4 times. Hmm. Oh, maybe I don't have KKNN. It's weird. Okay, let me try this again. Okay. All right. So it runs, okay, and it has, all right, these are all of the different splits that we have. So we took our training set, all right, so the original data had 572 observations. We took our training set with 429, and then it got split into, five folds, each fold having around 343 predictions and 86, or in some cases, only 85 in the assessment set. And with each of these things, we've made predictions and we can, look at all of them and, and specify any of these things, right? So we can, um, let's see, K&N results. So we can see, for for the different K, we had K1, K6, K10, K15, and we can see, how much error we have for each of these things. Okay. Um, And we can do the same kind of thing. We'll do a linear regression model as far as our recipe goes. Um, in this case, we're just going to make dummy variables, remove anything that has um, zero variance. Okay, we don't have to center and scale. I mean, we could, all right, impute the mean or normalize, but we don't have to. Um, so we'll have that as our recipe. Our workflow will just kind of combine the linear model along with our recipe, and then we'll ask it to again fit the resamples to train our model here. Okay, so as far as this, there's no tuning to do because it's linear regression. We don't have any hyperparameters. We don't have to determine how many neighbors or how many variables or whatever. So we have no hyperparameters to worry about there. So we're just going to call fit resamples. Okay, so we establish our recipe, our model definition, establish our recipe, um, create a workflow, and then we will fit it to our resamples there. So that's that. And then our results are here. And we can also take a look at the metrics. We can see how it has performed. Okay. And then finally, we'll do the same thing for support vector machines. And here we're going to have a grid with six values here as far as um, what we want to tune. Okay, so these are just very kind of simple things. Perhaps in your when you do stacked models, you can have an even larger grid. Okay, so we have the cost parameter and the sigma parameter as far as values that can be tuned for support vector machines. But and here we're only doing, a total of six different combinations. And probably in yours, you'll probably want to try out even more. But you have these different kind of tunable things, and you set up your grid. Here's the recipe. The recipe has um, a few more steps here. Make dummy variables, remove anything with zero variance, impute means. And here we have a correlation filter, getting rid of any kind of variables that have high correlation. I don't think it actually makes a direct difference in our data set, but who knows? Okay. So there's our workflow, and then we're going to run TuneGrid. And here we're going to have six values in our tuning grid. But again, you can um, try out even more here. Okay. All right, so it's running. All right, and then we have our results here, and we have, six different, you can see under metrics, we have six different models that we've checked, okay, across, five different folds. So here I can do collect metrics for SVM results, right? And so we can see we have, these are the different combinations as far as cost and sigma, the six different values here, and we can see the different kind of performance. So it looks like, we have different performance values there. Okay. And so here we have all of our different results. We have the SVM results. We have the um, linear regression results. So once we've kind of trained all of these different models and tested them out, okay, we have all of these different results, and we want to, we're going to define a stack based on this, okay? So we have these different kind of candidate models, okay? Using kind of cross-fold validation, and we have kind of a sense of how they're working. And so we're going to take all of the results and form a stack. Okay, so as far as forming a stack goes, is we're going to take all of the results. Okay, so you can see KNN results, and these are the results of tuning the results using cross-validation. Okay, and we're going to add these as candidate models. So we're going to form a stack, add candidates from our KNN, linear regression, and SVM results. This is going to form our tree frogs data stack. And so when we ask, what are the details here? Okay, it says it's a data stack with 3 model definitions, okay, and 11 candidate members, which is exactly what we have. So KNN, we have 4 model configurations because that was our, when we did our tuning grid, we said try out 4 different values. Okay. And, you could expand this to be, 40 if you want. It just would take your computer longer to run and process. Okay. And then here for support vector machines, we have 6. And so it says, yeah, you've got 6 model configurations. For linear regression, we only have 1. Okay. And so this is um, our data stack, 11 different candidate members. And we can say, okay, well, you know what? I want to take a closer look at each of these things. So you can do as Tibble here if you want, the tree frogs data stack. Okay. And here it says these are, let me just show you control. Let me do capital V view. Okay. So this is what it looks like. Okay. So remember, our training data has 429 observations. And so when you look at the stack, there's 429 observations. And so this is, let's see. Okay. So it's the same kind of values. So, this observation had 442. So it's the same observations, 360, 355. And, when we fit our model, we're trying to predict 442 based on values in the data, control, low, I don't know, age, time of day, right? And based, the next thing we have this, and its treatment was control, reflex, low, age is this, time of day is this. And so, based on these 4 variables, we're trying to predict latency. Okay. Now, we had KNN predict latency. We had 4 different KNN models predict latency. We had linear regression predict latency. We had the support vector machine predict latency. And so we have these different kind of things. And so now it's like, can you predict latency based on these 11 variables? Okay. And these 11 variables are highly correlated, but still, can we predict this output based on the other columns. Okay, and that's basically what the stack represents. So the stack says, okay, we've taken basically what the first KNN model predicts and what the second KNN model predicts, and so on and so forth. Um, it takes all of these different things and says, okay, based on what each of these things are predicting, can we still predict latency? All right, so it's kind of abstracting it to a higher level here. All right, so that's what we have, and then so now what we do is we take this thing and we call blend predictions. So we're going to take our tree models stack and we're going to call blend predictions on it. So our tree frogs stack, we call blend predictions and we'll save it back to tree frogs um, we'll, as our model stack. Okay. So that finishes. We can take a look at this and says, out of the 11 possible candidate members, the ensemble retained six. And this is kind of how it does it. It uses lasso to try to do this. Now you can change how this wants to perform, and you can. There's a plot like these are diagnostic plots that say like, okay, these are different values you can try out as far as how many members is it going to keep and things like that. Okay. It says to make sure we have the right trade-off between minimizing the number of members and optimizing performance, we can use the auto plot to kind of see this. And, we're not seeing huge amounts of average number of members. So I guess if you have more members, I guess the RMSE goes slightly down. But I mean, we're going from 4.12 to 4.16 members. So not a huge not a huge difference. If you have more members, I guess higher RMSE, fewer members, lower RMSE, maybe, but there's still kind of a bit of spread. Um, but you can try things out with different penalty parameters. So as far as fitting lasso, you have penalties for complexity. So as you increase your penalty parameter, Lasso is going to try to tend to fit fewer, use fewer of your predictors and make a simpler model. Um, but anyway, these are options that you can do as far as blend predictions go. And so this is the weighting coefficients as far as um, the different members. So you have uh, the support vector machine has the highest stacking coefficient, and linear regression has the next highest, and so on and so forth. Okay. And so anyway, we can take this and we'll fit the candidates, all right, um, to create our tree frogs model stack. Okay, so we have this, we blend our predictions, and then we'll take our resulting models and then we'll fit our members here. So after we call blend predictions, it does that. And then these are the six. Okay. So it says retain six. So it's just showing us the same kind of results. Members have not yet been fitted. And so we'll call fitted. And then so now our model has been fit. Okay. And we can ask collect parameters. Uh, and you can see exactly which ones were kept. It says to identify which model configurations were assigned, what stacking coefficients, we can make use of the collect parameters, and you can see exactly which ones were kept. So you can see, okay, SVM uh, results 1_4. That was the one that was kept, which had this cost and this sigma coefficient, and the corresponding stacking coefficient here is 0.896, and that shows up right there. Okay. And you can see, okay, the other ones that were kept was this one, these ones were kept. And you can see exactly, what were their kind of coefficient weights, zero point 0.2 and 0.103. Okay. And these ones got zeroed out. And then so now we can say, let's go ahead and make predictions. Okay. So as far as our predictions go, we can take our model stack. Okay. And then we run it on our tree frogs test. Okay. So we can do that. And these are going to be all of the predictions it's making. And we can compare that with actual tree frogs test. So this is the actual values for latency. And so we'll attach our predictions there. And so now we can look at our predictions. And so we have our the actual value here along with our predictions here. And we can create a plot on how well our predictions are compared to our the actual values, right? And so that's what this ggplot is. And what you want to see is you want to see, high correlation between these, and yeah, it's better than nothing, I guess. Um, so this is what we have here. Okay, if we say what is the correlation between tree frogs test. Okay, so we're getting correlation of around 0.619. So, um, you know, decent, okay? Improved performance there. It says looks like our predictions were pretty strong. And how do they perform? And then we can kind of just see um, how do they compare to just any of the individual things. Okay, so we can say, all right, what were the member predictions? Okay, and we want to kind of look at each of these. All right, and so we can see this is what our prediction is versus what the member predictions are, right? And so we can see this, our final prediction is kind of a blend of these other ones. So, each member there were we have uh there's one more column. Let me see if I can fit this in here. Okay, so you have the 6 candidates here, and they get blended according to these wherever our coefficients were, right? So the final coefficients, I think, were 896 for this model. So we take this model and we multiply it by 0.896, and we add them together, do a linear combination of these things to get our final prediction here. Um, and you can um, kind of compare each, its own kind of performance versus any of these one predictions. So if I said, all right, member predictions, what's the correlation between member predictions and say latency? Okay, so our overall, when we look at the overall performance, its correlation is 0.619. If I take any one of the individual members, probably not as good. Okay. All right. So KNN results 1_3 has that. 1_4 has that performance. We can say, what about linear regression? Has 0.602, and then SVM results 1.57714 has that, and 1_6 has that, right? So each of the individually, um, they're, how well do they predict the latency we're getting, 0.597, 0.601, 0.602, 0.577, 0.527, 0.595. It's okay, all right? But then by kind of blending them together to make our um, overall stacked prediction, we're able to squeeze out a little bit higher performance of 0.619. So basically, we're just taking each of these things, all right? So we have six different well, we had 11, and then we chose six of them. And then from these six models, we blend their predictions together to get something even better performing. And that is an ensemble or a stack here. Okay. And I do think it will improve your model prediction performance. Right now, I'm not sure, what you're doing um, on Kaggle and what kind of progress you've made, but I do think by using a stack, you will be able to kind of squeeze out additional performance there. Okay, that's all I have for today. Take a look at the documentation with stacks, and it is, again, going to be kind of a final step. So you build all of these different candidate models, and then you combine them all together to try to build an even super ensemble model there. Okay, we'll wrap things up here. Good luck as you guys continue to work on your projects. So yes, continue working on your regression projects and improve the performance there. And then please also do start to take a look at the classification project. All right, thanks for joining me, and we'll see you guys maybe on Thursday. We'll see if they turn the AC back on. If it's back on, we'll meet back in person. Otherwise, we'll meet online again. All right. Thanks, everyone.
Thank you.